Well, good morning. It's indeed a pleasure to be with you all. I'm Praveen Frenyas. I'm from VIT University Chennai campus. And as you can see, I'm the presenting author and the second author of the paper, Compressive Sensing for Digital Holographic Microscopy. The general outline of the program will be like, I'll talk about digital holography and why I use digital inline holography microscopy and the reason I applied that for compressive sensing and general thing, what is compressive sensing you need to know, results and discussion, and finally my references. So digital holography, and majority of you have been knowing it, that digital holography is just a two-step process in which the first step, it involves you optically record the object, the hologram, by means of a charge coupled device or a CMOS sensor. Once you optically record it, then you give it to a computer, and that's the strength of holography. You numerically reconstruct it using the scalar diffraction theory. The main advantage of going to digital holography is that there is no wet chemical processing. Conventional holography needs more stability. Those things are there, but in digital holography, I can almost do it in real time. And there are different types of geometry, like inline, off-axis, Fourier, fractional Fourier. But we stick about inline holography. Inline holography is that you have the object and the CCD, they all in the straight line. The main advantage of going to the inline holography is that you can able to have use the entire bandwidth of the CCD. And if you apply digital holography to microscopy, that you call as digital holographic microscopy, and there are many advantages. That main thing is it's low cost, optical aberration. Since the strength of holography is in the computational part, you reconstruct it. Everything you can remove by using the numerical reconstruction method. I quote, lensless inline holography using spherical reference beam, referred to in the literature as digital inline holographic microscopy, end quote. And this is generally used for high resolution imaging, and we generally apply it for characterization of materials like microarray lenses and polystyrene beads. Also now it has a very good application in life science. They're used to study microbes. This is the general scheme in which we use. We have a 532. Okay. 532 nanometer laser. It passes through a microscope objective. A microscope objective is just a magnifying glass with short focal length, and you pass it through a pinhole. The pinhole, what it does is it removes the higher order aberrations, the optical harmonics, it removes it, and finally it's in our case it's polystyrene beads. You can see probably O is there, right? It's a polystyrene bead that falls on the object and it diffracts, and it splits into two: one spherical reference way, the unscattered spherical reference way, and the object way. You recorded the CCD. In our experiment, we use the distance from point source to the hologram plane is 29 millimeter, and from the point source, the pinhole, to the object, it's 2 millimeter. The distance between the sample and the hologram is 27 millimeter. The general thing we use for reconstruction, once we have the object, the hologram recorded, we use the Helmholtz-Kirchhoff integral. Here, the three things you need to keep in mind. One is the distance between the pinhole and the sample, that is Z, in our case is 2 millimeter, and the distance between the sample and the hologram, that is 27 millimeter, and finally K, Wave number, lambda, 2 pi by lambda. So the reason for why we go for compressive sensing. This is a general hologram. This is the recurrent hologram, and it's a 550 cross 550 contrast hologram. You get a contrast hologram by after obtaining the hologram, you remove the object, you record it, and you process by the equation h minus h naught square root of h naught. It will give you a better. It is for better illumination, optical corrections. And most of the specimens, microscopy specimens, are sparse in nature, and the direct, and then you will be seeing it. When you use a direct method for reconstruction, actually you lose the phase. This is compressive sensing. I quote, "Many natural signals are sparse or compressible in the sense that they have concise representation when expressed in the proper basis." End quote. And this is about the compressive sensing. Compressive sensing, what it does, you don't need to have the entire thing to reconstruct it. If the signal is n dimension and the signal and it is S sparse, you don't require the entire n sample space. It's enough that you have k sample. And conventionally, you say the Nyquist criteria that it should be, the signal sense should be greater than 2fm. But whereas in compressive sensing, it does not require to be the maximum signal, and also in conventional method, the Nyquist actually you use a low pass filter to recover your signal, whereas in compressive sensing, you go for convex optimization. This is the algorithm. You can see compressive sensing is an iterative algorithm. You reconstruct it with an assumption that the original signal is sparse in nature. If you see the equation, it denotes the incomplete measurement of the complex object weight, x, and x is nothing but phi by s, and phi denotes the specifying matrix, and psi is the sensing matrix. But in our case, since we moved with an assumption that microscopes objectives are generally sparse in nature, we don't need to go for a specifying matrix. Instead, we removed it and we use phi in our case as the inverse Helmholtz-Kirchhoff integral, so that we get back the original image. The algorithm which we use is the GPRS algorithm, and this is just a two-step process. Process A tells you how we retrieve the complex object wave, the spherical beads in our case, using the Helmholtz-Kirchhoff integral. It's an inverse Helmholtz-Kirchhoff integral. And process B, A inverse. Process operate A inverse, apply a Helmholtz-Kirchhoff integral to get the hologram. It's like a trial and error method, complex method. And because tau, you need to choose tau to better get your results. And as you can see the result, the figure A, you have the magnitude of the direct Helmholtz-Kirchhoff integral, and figure B represents the phase. Figure B doesn't talk much about the phase. The phase is getting corrupted. We assume that because of the natural sampling recording method, it is observing, it's happening. But whereas when you use a compressive sensing method, you can directly see there is an improved phase. You are able to see the reconstruction when you use this GPS algorithm. And finally, to conclude, that compressive sensing is essentially a potential algorithm which can be used for an application like microscopy for a better reconstruction of phase and intensity. These are my references. Barton is the one who pioneered in inline holography, and Cruiser played an important role in that. And in compressive sensing, Mario and Cadis, they were the lead player. And I'd like to thank the Optical Society of America for the Student Leadership Conference grant, and I'm thankful for the OSA Foundation for the Student Travel grant for this 40 year in optics.
Questions? So I missed one point at the end. You were saying something about it was naturally sparse. Why can you assume that the object is naturally sparse?
Because it's see the hologram there.
Because it's just the beads. Okay, it's an object that might not be.
Yes.
Okay, I understand. Any other questions? Okay, if not, let's thank our speaker again.
Thank you.
And is the final presenter.